So video 4 for assignment 4 research methods, the final stage of quantitative data analysis. Again, numerical data and the statistical test that we can use to get some meaning from. We're down now to the last bit of the unit specification, so the yellow data analysis information there, and basically there you've got listed a whole load of statistical tests that you possibly could use. However, some of these are really not level 3 standard. At degree and at masters and PhD level you might use all of these. We're going to look at one or two of them and you'll have a go with those. Same assessment criteria and same assignment scenario. And we've covered these 3 stages so far, and we're now going to look at data analysis, the inferential statistics. Descriptive statistics, as you may remember, are a little bit more superficial, a little bit more, as it suggests, descriptive, and from the results you get from these tests you can infer meaning, so we get more depth of information from statistical tests in this section. So, what are inferential statistics? How do you test for difference? How do you test for correlation? And how do we use what we call decision trees to decide which test we should use? So those are the things that we're going to cover in this video. So inferential statistics are twofold really. One, they assess the ability for you to expect an outcome, so the probability of something occurring based on the results that you got. The second thing is you might test a certain population, and then hopefully from your results, if you have a valid and reliable protocol and set of results, you can then generalize your findings to the broader population that your sample was representing. And as I suggested earlier, inferential stats are more analytical. They don't just describe what the data is, they look at meaning. And you may remember from video 1, task 1, this sort of analysis, this sort of testing is all about the null. Do you accept or do you reject the null hypothesis? And your results from these tests will enable you to do that. So it gives us much firmer conclusions, and it also shows what we call if results are significant or not. So what is a statistical test? Well, it's one of the tests that we use when we're looking for relationships between two sets of data, or we're looking to see if there's a difference between two sets of data. But it's not enough just to get some results and go, yep, they're different, therefore it's really sort of informed us that there's a difference. That's not enough, because it could be that it was just luck that there's a difference, or the differences that you can see are quite small, and we need something that gives our results a bit of clout, a bit of trust. And so we use what we call a level of significance in our testing. And this level of significance we use to determine if our results are gained and are likely to be just a fluke or luck, or if they're more credible and we can trust them, we can rely on them some more. So again, there's a little bit of a process in terms of determining actually which test from that list of, I think at least 10 that we saw in the unit specification. And we need to make some decisions. We need to know about our data. And the information we need to know about our data is this. Is it parametric or non-parametric data? So is it normally distributed or not? Are we looking for difference or a correlation in the two sets of data? What classification of data is it? Now, as I've suggested, you're more likely to be working with continuous data. What subjects did we use to collect the two sets of data? Was it the same subjects that did two different things? Was it matched pairs, or were they independent groups that you collected data from? And what we can do is we can use what we call a decision tree to walk you through the process of knowing which test to do. Parametric tests are used when data is normally distributed and there's continuous data, so it's likely that you will do parametric difference or correlation tests. and non-parametric tests are where there is not a normal distribution or where you have a different kind of classification of data or levels of data. Just to remind you, this is what a normal distribution would look like, the bell-shaped curve. So testing for difference. There are a couple of variations on how we might look at two sets of data and look for difference. So differences are actually tested looking at the means of the two collections of data that you have, two groups or two conditions. So you might look at one variable and use two different groups of people, or you might look at the same people doing two different activities or two different conditions. Either way, we've got two sets of data and we look at the means of those two to see if there's a significant difference between the means. An example might be VO2 max values for smokers and non-smokers. So we've got our smokers who did it, we've got our non-smokers who did it, we get the VO2 max values, we get the mean of theirs, and test for difference between them. Or there might be what we call a repeated measures data collection. So this is an example which might illustrate this. If we were looking for the difference between free throws scored with and without an audience, we would use the same, let's say 20 subjects. They would shoot without an audience, they would shoot with an audience. The means of their scores with would be compared to the means of their scores without, and if there was a significant difference, it would be apparent from our statistical test. So this example, we've used the same people and done two different conditions, and that's called a repeated measures test or experiment. Another thing that's commonly done is we call test-retest, where we look to see if an independent variable affects a dependent variable, so the thing that you're measuring and the thing that you're going to manipulate. So this example could be good to help you understand that. If our dependent variable, the thing we're going to measure, was a VO2 max score, we could measure a group of people at the start. We could then give them a training program over 6 weeks, which would be the thing we're manipulating, the independent variable. And then we retest the same measurable thing, the VO2 max score, afterwards. So it's test, retest, to see if this independent variable, in this case the training program, has had an effect on their VO2 max scores. So again, looking at which test to use to test for difference, we know that we have to determine if our data is parametric or non-parametric, and if we are using the same subjects and using matched subjects to gain the two data sets, we would use a dependent or paired t-test. So the same subjects means that their results will be paired. If we're using different sets of groups, so between groups, we would use an independent t-test. So it's likely that you will use, I would probably suggest this paired t-test in any case, but it could be an independent t-test. If hypothetically your data was non-parametric and you used the same subjects, you'd use the Wilcoxon match to pairs test, and if it wasn't the same group of subjects, you'd use the Mann-Whitney U-test. But as I said, it's less likely these will be relevant to your experiments. Now, this very visual diagram here is what we call a decision tree, and this is quite helpful in determining which test we got to. Now, I gave you the answers on the previous slide, but this illustrates how I got there. So it's almost like a series of questions. Have you got two or more sets of data to use? Yes. Is the data nominal or continuous? If it's nominal, you would use chi-squared test. Are data likely to be continuous? In which case, we then go on to the next question. Are there two categories? As in, are there two conditions? Yes, there are. Are the subjects the same sample group, or are they two separate groups of people? Now, it's likely you use each other, so it will be the same subject groups. we're going to assume normality of the data set, which means that we'll be using a parametric test, and because of this, the same subjects and normal distribution, you'll probably end up using a paired sample t-test. I can assure you that this bottom half, because this is more than 2 categories, we won't go anywhere near. That's pretty tough research method, so we can eliminate that. So this is our sort of decision route, and for the most part you'll start and you'll go on this route, and it's quite likely you'll end up doing a paired samples t-test. So looking at correlations in a similar way, now correlations measure if two things are related or if they correlate, and it can give you an exact value, an exact relationship, a quantifiable relationship. So is there a correlation between eating chocolate and waist size, just as a silly example. Now a correlation coefficient is this R value here, gives the level of relationship, so the amount of a relationship that two sets of data have. The R value can be somewhere between -1 and +1, +1 being a positive correlation, -1 being a negative correlation. Here are some other examples of possible correlation tests. So is there a relationship between sunshine and mood? Is there a relationship between exercise and weight loss? Is there a relationship between time spent at a computer and postural issues? So correlations come in different sort of shapes and sizes, if you like. This linear diagonal line upwards would represent data that showed a strong positive correlation. So this is a scatter graph or a scattergram, which you can easily plot to give you a sort of a starting point in determining if you think there might be a correlation. This reverse one, and this means that as one value goes up, so does the other absolutely equally. This graph shows a negative correlation, a strong negative correlation, so where one goes up, the other goes down. So starting high, going lower. You can see on these two here, you've got a weak positive or a weak negative. So there's an element of correlation, but it's not as strong as this. And down here, the indication here is that these are quite random, particularly this one here, quite random, and does not show any correlation at all. No relationship between this axis data and this axis data. So +1 is a positive, -1 is a negative correlation, and the larger the R value nearer 1, the stronger the correlation. If you have a 0 value, so nearer 0, that indicates there's no correlation. But what this doesn't tell us is that one is definitely affecting the other, which way round the relationship is. So is it that chocolate eating gives you a larger waistline, or it's not causal? You can't assume causality from this results. Which correlation tests to use then? If your data is parametric, you'd use the Pearson product moment correlation coefficient, and this is the one you're more likely to be using. If it were non-parametric, you use Spearman rank order correlation. All a bit of a mouthful. And again, we've got a decision tree that we use. We can ignore those irrelevant sets of data. So from here, going this way, we're assuming normality, and it's likely therefore that you'll use Pearson's product moment correlation coefficient test. Just to recap, we've gone through what inferential statistics are. They're much more meatier, informative results compared to descriptive statistics. How you would go through determining which test to use for a test for difference, how you would determine a test for correlation, and we've had a look at the decision trees you would use in doing that.